Okay, if you have any questions or something to ask, you can ask now. Also, regarding anything from last week, uh, last week assignments or other discussions which we had, anything probably not understood or something, having any issue at any other place, like, uh, I mean, maybe in your assignments. You can ask any questions you have. Yeah, are you going through the lectures? Uh, hello.
Yes, sir. Good evening.
Yeah, yeah, good evening.
Sir, I have a question. In classical, the topic is in classical ideal gas
Uh-huh.
and phase space method.
Phase space method. Okay.
Yeah.
Uh-huh.
So, in this topic, I had a question.
Okay, okay. Yeah, yeah.
I
Good.
did not get it properly.
Okay, so what was the question?
Uh, there is a one equation,
Uh-huh.
total energy
Okay.
equal to
Uh-huh.
h prime square upon 2 m a square, summation I equal to 1 to n
Okay.
n square p
Uh-huh.
uh, comma I.
Okay. So could you like, is there any way you can share me that equation or something? Uh, like maybe in the chat box or something.
Okay, sir, I will try that.
Uh, like, I'm not properly able to get your equation, like, or anywhere that is given in assignment, or
No, no,
or it was given somewhere in the lecture video you were talking about.
no, sir. In that particular topic, I am asking.
Yeah, in that topic. So where did you get that equation which you are telling right now? Uh, it's from some book you are telling,
No, 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 no.
or
Lecture in lecture itself.
oh, okay, in lecture video you mean, right?
Yeah.
Okay, okay, yeah. Like, could you tell me which lecture video? Like,
Oh, it's lecture Maxwell Boltzmann distribution.
okay, Maxwell's Boltzmann distribution. Yeah. Uh, so week one, right? Or week two?
Yeah, week 2.
Okay, week two. So, so exactly at which place?
In classical ideal gas phase space method.
Okay. You're talking about total energy. What was the?
Total energy of all the molecules is.
Okay, okay. Let me check. Yeah, yeah. Total energy of all the molecules. Yeah. What was the problem here?
This question I did not understand properly. So where it's come from?
Okay. So what is explained before here? P square. So energy, that energy of molecule is given as T square over 2m. So your
Yes.
uh, then then basically what is happening here? So p square, if you remember, I mean, you can write it as like in semi-classical, or from the momentum can be written as something, Planck's constant times wave number, something h bar k. Uh,
Yeah.
let me, uh, the phase space may be written as xp, uh, xp. So you will see that before that, like, I mean, the phase space size, it is actually given by x comma p. Hello.
Yes, sir.
Uh, so x will be, it is written as like for a like I mean, from 0 to nl, you have nx.
Mm.
Then from infinite, I mean, your momentum goes from minus infinite to infinite limit.
Yes, sir.
So within there, your momentum is given as h bar prime over a times np. So h bar over a, I think it is your uh, momentum, and np is your total number of states. Np. So like, I can just I mean, uh, uh, like, I have to go through this entire thing, first of all, but otherwise you can see that, like, you can write p square as something, let me show you right here. So I mean, so P is something like, from what you say, like from a de Broglie hypothesis, from de Broglie relation. Like, momentum can be written as something h by lambda. Uh, so you know that.
Mm.
So from there you can further write here. So if I multiply and divide 2 pi, like in the denominator and the numerator, so I can get h bar times k. So that is, uh, h bar is basically a reduced Planck's constant, h by 2 pi. But here I think, uh, so p is written as h over lambda. So this lambda which I'm telling here, so that is given by a, and np is your some total number of uh, particles. uh, Np, what is np? uh, so np is something, do you know what is np?
No, sir.
Okay, so like I have to like check this video properly, like, to exactly get what np is, or maybe just let me check. But in terms of relation, like, you can understand that momentum can be written as something h by a. A is your that size of the unit. So it is like, I mean, your phase space with your uh, position dimension, I mean, your phase space, like, I mean, your instructor, which he is explaining in the phase space description. So your x was varying from 0 to l. 0 to L. So your x varies from 0 to L, and within like 0 to L, so it is divided into uh, small a units. So it is like total L is given by NL times A. So momentum is also something, I hope it is written like that. So so this A is basically your small uh, element length. So that is why so this lambda is taken to be A. So your momentum is basically given as something h over A, and this NP is the total number of uh, I think again that is also a small uh, and I mean just like how you have NL, so your momentum is also something given in terms of NP. So that is why your total momentum is something NP h over A. So did you able to get a rough idea how this momentum can be
Oh,
defined as NP?
yes, sir.
So are you getting right how
Yeah,
it is h over A, right?
yes, sir.
Okay. Like NP, like, I have to check it again completely the whole thing. Then I can tell you. But that relation is correct. So then next uh, yeah, that was your what energy per each molecule. Then if you calculate the total energy, so the total energy will be the sum over P. So that is for any particle with momentum P, the energy was given by h prime square n p square by 2 ma square, right? and and when you so there are many particles with uh, uh, sorry, this is energy of each molecule. So for all molecules, so this there will be uh, all different NP, you have to sum them all. So your problem was this, right? Your
Yes,
Okay, so you are getting right how EP would be written as h prime square, not h bar. So h prime square by 2 ma square np square. So for total energy, you have to sum this over p. Okay,
yes, yes.
yeah, not over p, like so over I actually. So for
Yeah,
ith
I
molecule,
equal to.
it is given as EP. For all other there will be many I mean molecules where I would go from 1 to n. Okay, so any other question or something? Like I will go through exactly like what NP is. I uh,
No, sir. Thank you.
okay. Okay, so any other question, anything like anyone else have any issue or? Okay, you can tell me any other problem, maybe in assignments or also in the lectures also. If you have, you can tell me now. Okay, if not, we can discuss something related to I mean your some topics or problems from this week's uh, discussion which you have seen from your lectures. So, like, we can go through something about Gibbs paradox, and yeah. So before that, we can start with a basic concept about partition function. So, it is a very uh, I mean, a key element in your statistical mechanics, where this is like something very fundamental. Uh, uh, I mean, notion is a fundamental definition which you would be needing everywhere to describe your thermodynamical properties. So, and this is known as partition function. So, yeah, again, this you would have also seen in your lectures in your lectures as well. So your partition function, it is like a mathematical definition. So it is uh, like given as uh, something uh, denoted as z, and and this is defined as summation over I, zi times exponential of minus beta epsilon I. So your zi are basically your degeneracy, and beta is your uh, like your inverse temperature, uh, meaning your beta is your inverse of Boltzmann's constant times temperature. Then further you have uh, then further you have energy EI. So these are, so it is like, suppose you have a statistical distribution of different energy levels. Let's say epsilon one, epsilon two, uh, and there are like many particles. They are distributed in different energy levels, and let's say some energy levels have uh, uh, some distributions have I mean energies with I mean some levels have same energy, like here. So you have in epsilon 3 you have two degeneracies. So here corresponding to this you will have degeneracy 2. Corresponding to this you have degeneracy 1. So so that is what for some distribution like this you can define a partition function like here. So, so it's a mathematical element required to make probabilities add up to one. Meaning, like you will see that, like in the, I mean, so as we were discussing about different microstates for a given macroscopic, uh, for a given macrostate of a thermodynamic system, you can count, you can see that like there are various number of microstates. So, so in that relation, like I mean, if you statistically see, like for example, we can see I mean, a case where let's say um, uh, you have a um, idle gas, uh, or some, let's say you have a distribution of gas molecule. Uh, let's say there are uh, Ni molecules, uh, or yeah, Ni molecules occupy the ith state uh, with energy uh, epsilon I and degeneracy uh, Vi. So So then you can write that distrib- uh, so yeah, so you can write the distribution as Ni equals to, so this is from Maxwell's Boltzmann distribution. So you can write as Ni equals to Zi exponential of minus epsilon I over kbt, or that is only which I have written earlier, beta e epsilon I. So there will be some constant a. So if you have seen, like probably there would be some different topic you have gone through, like surely in your thermodynamic course, like there would be topic on kinetic theory of gases where you discuss something like Maxwell's Boltzmann relation. So uh, Maxwell's Boltzmann distribution. Uh, so in that distribution, uh, so that distribution only I'm writing here. So Ni is given as something, you will see some kind of constant that you generally get. So I mean, so this constant is something I hope you have seen, like could be something m over 2 pi uh, kt something, or whole to the power some 3 by 2. So there are like it depends on what kind of distribution, whether it's three dimensional, two dimensional. So you have seen that. So so with that, I mean Maxwell Boltzmann rule, you can define that your Ni would be your total distribution, or your molecules occupying your ith energy. So in that case, you can write this. So that is the Maxwell's Boltzmann law. So from there you can, what you can do, what you can write. So total uh, number of gas molecules. So uh, is n. Then your n would be summation I over ni. So this is IZI, and A will be, you can take it outside, and so you have epsilon I over kt, or that is A summation I zi epsilon exponential minus beta t, or minus beta epsilon I. Yeah. So so suppose if I yeah, if I take this ratio n over a, then that is given as summation I zi uh, exponential minus beta epsilon I. And this, you will see that it is basically equal to something, the definition which I started here. So this is what we call partition function. So this n over a is basically your partition function. So it's basically a fraction or a probability. So like I can, so suppose if uh, like if someone asks you about what is the probability of a particle, or a molecule with energy ei, so that probability would be something, you say that like it is uh, related with uh, exponential of minus beta epsilon I, because from Maxwell Boltzmann relation you will write that, because for Maxwell's Boltzmann relation, you know, for a particle having energy ei, there would be this many number of molecules obeying the distribution. So so the probability would be something proportional to this, but we know total probability must be one. should be conserved. So that means it has to be this probability has to be something exponential minus beta epsilon I over z, because z tells you that uh, uh, because z is summed over all the I, uh, like because you see that in z in the definition, so you see it is summed over all I. So that means it is giving you some total, uh, I mean, uh, a is arbitrary constant. No, like I'm saying that a is some constant. Uh, it is not arbitrary constant. It is also something to make your total. This is uh, suppose I mean there are ways to calculate uh, this a, so your a is also like part of your normalization constant, you would have remember in your kinetic theory of gases, there used to be something uh, like some constant like m over uh, 2 pi kt whole to the power something 3 over 2. So I'm talking about that is basically all those constant I am denoting by a right here. So because so it's just a normalization constant. So yeah. So but what I'm trying to say that even this jet the partisan function, you will see that it explains I mean how your uh, gas molecules uh, in the entire system. So you have total n number of gas molecules. So all those gas molecules, the total n number, how they are distributed at different energy levels. So that is why you have a summation here. So uh, so that is what like partition function you mean by. So now if you sum, so this is probability pi for a for molecule having IF EI energy. So for total probability, you will see that like it would be something summation P epsilon I, or that is pi. So then you will get one. So if you just call your probability to be something this exponential of minus beta uh, uh, epsilon I, then you will not see that probability is conserved. So when you introduce something like a partisan function, it is also this, I mean, a part of this normalization constant. So this is a normalization constant, which introducing this only makes your probabilities to go one. So yeah. So and you will see that I mean so there would be uh, so there are this partisan function. Now you can also relate with uh, I mean your number of microstates, which we discussed last time. So from that, like you can derive some various fundamental relations. So I mean there was like for example, as I was talking about Maxwell's Boltzmann relation. So there is a relation with this partisan function. So suppose if I can, so let's say uh, omega mb is your number of microstates for uh, mb means your Maxwell Boltzmann distribution. then you can write this. Uh, yeah, you can write this. There is this relation log of omega mb equals to summation I ni ln z uh, plus beta uh, uh, capital E. So this capital E, or you can write it as U also. So this is your total energy. This is your total energy. So there is this relation. So from here you generally you know that last time as we were talking about entropy, which we saw at the end, like this is related, entropy is related with uh, kb times log of omega mb. Uh, so that means your entropy can be written down in terms of your partition function here, and um, yeah, so it can be uh, nkb uh, ln z plus kb, so beta kb uh, e. So that is basically your um, so your n is basically total number of molecules. So you see the in the first part you had summation over ni, so that gives you n. So uh, then that is basically nkb ln z plus beta is your 1 over kbt. So if I write in terms of your yeah, so that is what I mean your relation is. So this your entropy, if this is how your entropy is related with your partition function. So so then there are other important relations as well. You will see. I mean, like from thermodynamics, you know, your you have something Helmholtz free energy. So this Helmholtz free energy is defined as this U minus Ts. So this E is basically your U. So maybe it's better you write it as U. So here also this is U. So then from here further you will find that f is basically given as minus kbt uh, ln ln z. So so ln z, so, so z is your yeah, so z is your partition function. This is how your Helmholtz free energy is related with your uh, partition function. uh, yeah, uh, in that way you can also write your you know, like I mean from this relation you also have something, uh, you also know that you can write it as uh, df d. So the differential forms are related like this. So from here you can also define. So you have something s equals to minus del f over del t. So these are your thermodynamic definitions at constant nv. So from here also you can write your relation between your entropy and your partition function. So f is your minus kt ln z. So yeah, so likewise you can like you can find out all the relation of your thermodynamic variables with partition function. So so we can maybe see an example here, a quick example. Suppose uh, the free energy of a gas and of a gas having uh, n particles in a volume V and at a temperature T is uh, F n cavity ln n naught V cavity 5 over 2, then this is over n. So so your n naught is some constant, uh, constant. Then you find out the internal energy. So so you can start this out with free Helmholtz free energy as something F is given as uh, yeah. Yeah, you start out something, you can write your Helmholtz free energy as F equals to, which is given this thing, uh, N cavity ln uh, A naught V cavity whole to the power 5 by 2 N. So this is given for you, this Helmholtz free energy. So you can write it as cavity uh, ln uh, um, so so this whole thing uh, then to the power n. So so just using the property of log. So now you can compare the definition that we mm, which we have used. Uh, so the definition was, I mean, which we just discussed between Helmholtz free energy and the partition function is this. So your partition function, you can now uh, your so basically your uh, ln z is basically negative of ln then inside everything what you have. So this is your partition function. So now to calculate your internal energy, so so you know uh, your internal energy as I was talking about thermodynamic relation is given as F plus Ts. So that is equals to f minus t um, f minus t uh, yeah, your s is given by this, so you can write that as uh, del f by del t uh, at constant n v. So from here you can calculate your uh, total internal energy. So you know what is F. You know for F you need L and Z. You also got what is L and Z. Then from the next thing is you have to take the derivative of F with respect to T uh, by keeping n and b constant. So from here you can just straightforward you can just calculate. You have to just evaluate the derivatives and you have to calculate. So you will find out. You can check this out. So from here you will find u will be equal to something uh, minus 5 over 2 n cavity. So this is what you will get. So from like I mean this definition of partition function, you can calculate all your thermodynamic properties or thermodynamic quantities. So that is basically the message, and we'll see how using this we'll also talk about something more about Sackur Tetrode equation and how that will help you to resolve this Gibbs paradox, and yeah, we'll see. So, but before that, if you have any questions or anything, if you didn't understand, any question, anything, or did you understand all, or any problem? So in this question, you see here, like we didn't have to calculate this. I mean, from the definition of partition function, like the partition function definition has been introduced here. I mean, at the beginning, which was this summation vi exponential minus beta exponential minus beta epsilon I. So without using it, like it was already something said in the question that your free energy is already uh, written as something logarithm of this. So with that we have taken that is some form of definition of partition function, and using that we did. So we didn't have to exactly calculate what this partition function here. So but the idea was to, like, if we have some partition function z, or if it is related with any of the thermodynamic variable, then you can calculate everything. So like last time also, as we found out, like anything is if you find, if you can able to find out the number of microstates of your given statistical system, you can easily relate it with entropy, because the entropy is logarithm of omega. omega is your number of microstates. And once you have that, you from entropy you can calculate other like thermodynamic variables, just like how we've been using this thermodynamic relation and so on. Okay, if you have any questions, you can say, or maybe we can see further ahead. There, if you find any other question, you can look. Uh, uh, yeah. Okay. So yeah, as we were talking about partition function, which is defined in this way. So suppose like uh, if I have a continuous energy distribution, so in continuum limit, so this is like uh, uh, as I as we have been understanding this definition as some different energy levels are there. So this is epsilon 1, epsilon 2. So it has degeneracy B2 equals to 2, and this has degeneracy 1 and epsilon thing like this you have all. So, but these are all your discrete distributions. So for continuous distribution, for continuous distribution, uh, you so continuous. Uh, Let me write this bit precisely. Like for continuous energy distributions, your partition function can be given as something 0 to infinity, and your this will be your degeneracy will be written down as something as density of states exponential minus beta epsilon d epsilon. So this is something you might be again familiar with this. Uh, this is density of states. So this you see this in other places also, like in your courses of semiconductor or maybe some other place. So this is the same idea here, density of state. So this is just suppose if I have a non-degenerate system, uh, like classically as we know, I mean for uh, distribution of like classical type particles or like in three dimension, this is something maybe just for information I can write it down. This density of state times d epsilon can be written down as 2 pi v h bar q, which is reduced Planck constant, 2m 3 or 2 epsilon half d epsilon. So but if you have non-degenerate non-degenerate system, then your d epsilon is basically 1. So then you can just simply write your partition function as exponential minus beta epsilon. So your degeneracy is for a non-degenerate system is your degeneracy. Like for as in discrete case, we were looking like zi like z1 was 1, z2 was 2. But if it is like if it is non-degenerate, so for non-degenerate, it would be something every state would be having only one levels, no multiple levels with same energy. So it would be like that. Uh, and also you have a like yeah. So from here, so you can write exponential of uh, exponential of minus beta epsilon. You can write it as beta p square by 2m. So this is your uh, energy of a molecule. So and you are treating non-relativistic. So let's say for a non-relativistic system, because you can write energy equals to p square over 2m if the system is non-relativistic. Then in that case, so so now suppose probability of a molecule uh, having momentum p and p plus dp is equals to uh, number of cells in 60 phase space. So your 60 phase space means you have x, y, z and other momentums px, py, pz. So they constitute a 60 phase space. So then if that is the case, you can write it down. Your partition function is something this uh, 1 1 over h cube. So the h cube is the volume of each cell. So this is the like I mean here I am using the phase space idea, uh, the classical phase space idea of partition function. So um, then I can write it as uh, integral dx dy dz. So this is a volume integral over space, and similarly you have to do volume integral over momentum going from minus infinity to infinity. So this is now exponential minus beta over 2m, and your p square is your magnitude of momentum. So that is px square, py square, pz square. So then so now this is you have to integrate over dpx, dpy, and dpz. So so now you get partition function something b over h bar cube. Uh, uh, so you have to integrate. Uh, so integral of over dx dy dz, the volume integral is some volume v. So dy dz, then If you have any questions or something, you can ask. So yeah, this is minus beta over 2m px square py square and pz square. Then you have to integrate this out like variable by variable. So first you see, you try to integrate what is uh, value for dpx exponential minus beta px square over 2m. And I hope you are familiar with this kind of integrals. These are like your gamma integral type integrals. So gamma function definitions you have to apply here. So so this is first you apply. I mean you see that this is your even function. So for a given even function, you know that we use the integral property of twice of the interval, one half of the interval. You integrate it out the even function. If it is a odd function, you know it will be zero. Then yeah, then here you just apply. Uh, so what is like known as your gamma function definition. Uh, so or or maybe you just like to evaluate it. Let's take a variable xi, which is equals to dpx square over 2m. Then uh, so you will find dpx equals to m by 2 beta square root uh, xi minus half dz. So so then if you um, put that in this integral, you will have 2 2m over beta uh, 2m over beta, that is within square root 0 to infinity exponential minus xi to the power minus half dz. So so now you will see that so this is a very standard gamma function integral of order half. So this is like gamma 1 by 2, which is something like given as uh, um, root pi. So so here you can write your finally uh, so your value for the integral will be this. So so similarly you will get three factors of it because you first did this integral. So so uh, um, so this uh, so this is your 2m by beta, and similarly the other integrals are also same. That would be with respect to dpy and exponential minus py square over 2m. Same thing you will find. So so that will also give you uh, square root 2m pi over beta. So in total you will find uh, so you will find your partition function v over h bar cube uh, or v over h cube 2m pi over beta 3 by 2 or v over h cube 2m pi kt 3 by 2. So yeah, so uh, this is also known as single particle partition function. Uh, so uh, um, yeah, okay. So this is something that as we were discussing in the previous question, is basically related with this. Uh, yeah, this LNZ. Okay, so did you get this or any issue with this? Any problem or anything not understood? Uh, Now we can calculate the entropy as we have uh, discussed at the beginning that how this entropy is related with partition function. So, so yeah, right here. So we have seen how this entropy is related with partition function. So we can use this definition and the partition function which we just got. We can use that to calculate entropy. So, so your entropy can now be written. So let me write the definition again. LMZ. So it was like a beta kBu. It was like this, or otherwise I can also write your beta is 1 over kBt. So it would be just simply u by t. So this u by t. So yeah, then but yeah, uh, so before that, let's see what is LNZ. So we know Z is this. So what would be LNZ? Uh, so as I was telling, this is your uh, single particle. Uh, so this is your single particle partition function. So uh, suppose if you have a system for a system of an indistinguishable particle, then and non-degenerate, as we have said, like we are doing for only on non-degenerate cases, then your partition function, like as we said, it is given like this. So Zn epsilon. So this is summation I for exponential beta epsilon I. So uh, so this means uh, I can write this as uh, just moment. Uh, Let me verify this. Uh, yeah. So for a so at the beginning, which the uh, partition function, yeah. So here, as I was telling you about, so this is for you remember this. This is for your single particle partition function. Okay, your single particle partition function, and the one which we are seeing here. Uh, for now, this is your n independent uh, particles partition function. So, so for in that case, like your uh, partition function is actually like given something uh, in this way. Summation uh, uh, not let me write down to the power uh, n. Uh, if they are okay, let me remove this. So this is for independent sorry, independent particle. This is for if your particles are uh, uh, distinguishable. If your particles are indistinguishable, then your partition function can be written down as something. Uh, your partition function of your single particle, which you know, that is summation I exponential beta epsilon I, then this to the power n divided by n factorial. Uh, so now using this information, now what we can show here. So let's say we are working for a distinguishable particle. Um, um, uh, so your ln z. So what we are trying to do here is, so we are trying to get the, so we have already got the form of partition function. So in terms of temperature, volume, so you see here your partition function is a function of volume and temperature. Now we are trying to get what is entropy. So for entropy, we need to first evaluate what is ln z. So we got z in terms of volume and temperature. So we now need ln z. So and uh, z, as we are telling here, so z is, can be a single particle function and a n particle partition function. So so we are working here in n particle partition function. So for that, this definitions needs to change slightly. For as we know, whatever is the single particle function, the single particle partition function, you to take the power of that thing with n to the power n, that will give you the partition function for n independent particle if they are distinguishable. If they are indistinguishable, you have to take the power n and then divided by n factorial. Now you can take what is log of ln zn. So we are doing for n particle, n independent particle system. So that is why we need not just single particle partition function, but n independent particle partition function. So then ln zn will be this thing. So uh, you can do n ln z, uh, because uh, let's say we are doing for uh, distinguishable particles. So our system is distinguishable particles. Like our system is distinguishable particles. Then uh, so Zn uh, Vt is given as ZVt to the power n. So from here, so so using that, we can write ln Zn is equals to n ln z. So that means n uh, ln, and z is this, as we found out here. So z is this. So if you use that here, you will get, use the property of log, you will get ln v plus 3 by 2 ln kVt, uh, then plus 3 by 2 again ln m by 2 pi h bar square. So just you use the uh, logarithm property, and so now you got the ln z. uh, so so for entropy, you need L and Z. You also need what is internal energy. So now internal energy again, like if you uh, so as at the beginning, if you remember, uh, we have shown the relation of some thermodynamic property uh, with what? So yeah, so we have shown the relation of free energy with partition function. We also showed one relation of internal energy with free energy, and that free energy is related with partition function. So there is also one more relation here. So you can check this. So this here you can also write uh, your internal energy is also related with uh, kVt square uh, derivative of ln z over del t at constant n and v. So this two you can get this right from here only. So from here only you will get. So suppose if you write it like this, uh, minus t square del over del t f by t. So I'm just using the property of derivatives. So with chain rule and all that everything you can prove this. So then from here you have uh, yeah. So then f by t. Yeah. So from here you can show this. So your f is minus kVt ln z, and then you take the derivative. So if you take the derivative, you will finally end up with this relation. So are you getting or any question, any issue, anything not understood? Like if you are having any problem, you can just you can also speak. You can unmute and speak. So now, so we got L and Z. So we can also calculate what is U from the definition. KVt square del ln z over del t. So this is so since we are working with n independent partition function, so it would be Zn, and this is at constant n and v. So if you see, if you just uh, as we got what is L log of Zn, so you take the derivative and keeping n and v constant. So you're taking partial derivatives here. So that will give you 3 over 2 n by t. So you check this from here. You will find out that it will give you only 3 by 2 n n by t. So that means your u is uh, kVt square 3 by 2 n by t. This is 3 by 2 n kVt. So now finally you can get what is entropy. So you got uh, U as well. So, so now you can write what is your entropy. So, yeah, so your NKB, your log of uh, plus 3 by 2 NKB. So, so what you just have to do, so you use this. So let me call this as something equation P, and this is ln P. So this is your equation B. You put this in this equation, which is A. So you will get using B and C in A. So yeah, then you do some simplifications here further, um, like NKV. Uh, so like maybe like there are some simplifications if you do. Like I mean, the simplifications are like straightforward, or maybe just I can quickly write. So this is like ln bt 3 by 2 plus here you can see uh, you can take uh, so you can use the property of log. So kb can be multiplied here with m by 2 pi h bar cube h bar square. Then so if you do that, then further nkb, you also have nkb. Let me uh, uh, you can write this as ln 2 pi mkb over uh, okay, so this is into h square 3 by 2 uh, plus yeah 3, there will be plus 3 by 2. So just I'm using the property of log here, and then you can also write this nkb ln vt 3 by 2 plus ln 2 pi m kb, and the last term here also I can write what exponential of log of 3 by 2. So this in order to observe in a single log, so that is I'm writing this e inside h square uh, 3 by 2. So now you see your entropy is just given as nkb ln vt 3 by 2, then some constant c. So this is your entropy. Okay, so this is your um, Sackur Tetrode equation from which we will try to prove like your Gibbs paradox. We'll try to resolve that. So, do you have any problem with this or any any question here? Uh, okay, so we can try now. First, we'll solve mixing of two different gases. So, so we will calculate entropy using this definition, which we found out for the system of uh, two different ideal gases. Ideal gases. So you have a system of, let's say, you have system A and you have system B. They are different. So you have uh, V1 volume, V2 volume. You have, let's say, temperature here is T1. You have T2. Here N1 number of particles are there. Here N2 number of particles. Then the entropy in both the system, you can write it down as, let's say, entropy of the system A. So SA is given as N1 Kb ln V1. Um, so this two actually here temperature will be T. So this is in equilibrium. These two systems are in thermal bath. So let's say that the system A and B is itself in some thermal bath. So this is, they are kept or or maybe just I can write it like this. Uh, so this is thermal bath or reservoir. So they are in equilibrium. So the temperature is same for A and B, but you have different um, volume and number of particles in for both the systems. So no, so the entropy will be now N1 kb ln V1 T to the power 3 by 2. Then then yeah, you just use this relation which we got. So then this constant is the 12c. So that is the entropy for H system. So entropy for B system will be N2 kb ln V2 T 3 by 2 plus C. So, so yeah, you can also have different constants. So you have C1 and C2 because if you see, uh, so so C is related with 2 pi m kb over h bar cube. So m can be different. So that is why you can write C1 and C2. Then your uh, total entropy of the system uh, is S. Let's say um, total entropy is N1. Uh, yeah, it is just N1 ln V1 T 3 by 2. Yeah, it is just S1 plus S2. It is just the sum. But what will happen if, let's say, if I this uh, I mean the two systems you see, system A and B, they are like divided by some partition here. So now if I remove this partition, if I mix the entire system, so this is your partition. Uh, so suppose if I remove this partition and uh, so now you have so here you had some gas particles here, you had some gas particles here. So now you have gas particles all over the place. So you are mixing both the gases. So your volume will be V equals to V1 plus V2 because now you have the entire system. So this is your as usual reservoir, your thermal bath, and yeah, and your number of uh, uh, yeah. Now if you calculate the entropy here, what you will get. So uh, your entropy. So this, let's say you call this entropy as uh, um, initial entropy, meaning before the partition. Uh, uh, I mean before the partition was removed. Now you can calculate your entropy uh, after you removing the partition. That will give you this uh, N1 kb ln V. So V is your V1 plus V2. So the total volume, because uh, you have both the system have um, uh, because you have a single system which has the joint volume of V1 and V2, that is the sum of previous two volume V1 plus V2, so that is V, uh, then plus C1, then uh, you have N2 uh, N2 kV ln, this is V, not V2, this is T3 by 2 uh, plus C2. So now here if you see, so did you get this part? So so this is just like same entropy which was there initially. Initially your entropy was Si, which was simply N1 Kb ln V1 T3 by 2 plus C1 plus N2 Kb ln V2 T3 by 2 plus C2. But now your V1, your V1 and V2 will change. They will become V. Because why it will become V? Because I mean, when your earlier N1 particles were only within the region of V1, and also your N2 particles were only within the region of V2. But now you have uh, you have both N1 and N2 here. So they are all mixed after removing the compartment. So now your N1 particles, they are within the region of total volume V1 plus V2. Similar, the same as N2 also. N2 is also trapped inside a region of V1 plus V2. So so now so that is why your the final volume after removing the compartment, they will just become your volume will become v1 plus v2, because n1 particles will expand from earlier it was trapped inside v1. After removing the partition, it will expand from the volume of v1 to v2. The same, your n2 particles were trapped inside v2, they will also expand from v2 to v1. They will occupy the complete space, complete volume. So, so now if you calculate the mixed entropy, so the change in entropy, so that is delta S will be SF minus SI. This will be uh, so if you take the difference, so you will see it will give you uh, so the all the constants C1 C2, so they will cancel out. So what will remain is N1 Kb uh, ln uh, Vt3 by 2 minus ln V1 uh, Vt3 by 2, yeah, and then same way we have uh, N2 Kb ln um, Vt3 by 2 minus ln V2 T3 by 2. So, so this will now give you uh, N1 Kb, so ln V by V1 plus N2 Kb ln V by V2. So just using the properties of logarithm. Now here if you see um, this V and V by V1, so your V is basically V1 plus V2. So so that means if your V by V1 is greater than 1, uh, so this means V by V1 is greater than 1, then uh, then your log will be positive. So the same is here also. So that means your delta S is something positive, and it has to be because it's a irreversible process. So for a uh, uh, this is reasonable, or this is true for irreversible process. So you find your delta S is something positive. So and it is true that that system that we just discussed initially, which it was separated, and as we mix, it is difficult to get the system back to the original which it was before. So it's an irreversible process, and for the irreversible process, we know from the laws of thermodynamics that your entropy should always rise, and as we found here, the change in entropy is positive. So here we get the change in entropy something positive. Uh, Now, if you consider both the systems, uh, let's say mm, if n1 over v1 and n2 over v2 were same, meaning same density, if they were initially having same density, then you will find that your change in entropy delta S will be uh, n1 kb v over v1 is n2 kb n v over v2. So and this you can write it down. Um, um, so V over V1, you can write it down as so V1 plus V2 over V1. So this is 1 plus V2 by V1. That means this is 1 plus uh, N2 by N1. So from here, so this is basically V by V1, N1 plus N2 by N1. So your change in entropy will be KB N1 ln N1 plus N2 by N1. Similarly, you can also do the second term. You will find this will be ln N1 plus N2 over N2. So now, if you see uh, from here, you can get it if you had identical system. If you take identical system, that means N1 equal to N2 equal to N by 2, uh, let's say, and V1 equal to V2 equals to V by 2. So you consider this case. So what will happen? So as we were talking about the system, which was initially separated by a partition, so it has some gas. So if I call this as I mean subsystem A, and if I also call this as something subsystem A, so they are not like I mean earlier there were two different systems as we have discussed here. So we had A and B. They were different system because they had different volume and different number of particles. But now we have same system with same volume and same number of particles. So there are n by 2 particles here, n by 2 particles here. There are same. The volume here is v by 2. The volume here is v by 2. And then if you put them in the reservoir, meaning they are in equilibrium at constant temperature. Temperature is T here and T here. So thermal bath. This is now if you remove the partition here. Now if you remove the partition, what will happen? Um, they will all mix. So the you will have the system again in a complete in a big volume V. So again this is reservoir. So so in this case again you can calculate what is your entropy, change in entropy delta S, and this time you will see you will get it. You can just put I mean um, the values here. So n1 n2 as we already said it is n by 2. So if you put this in this relation again, this change in entropy relation, you will easily get your change in entropy would be twice of nkb ln2. But there is a problem here, and this is the paradox which we are talking about. So so this is uh, very questionable uh, in the sense because here we are talking about a system which had identical number of uh, particles here. I mean that these two copies, these two systems, they are actually copies of each other. So I mean you have n by 2 particles here, you have same n by 2 particles here, you have same. So this is V by 2 volume. So you have same V by 2 volume here, same V by 2 volume. So they are exactly identical. So that is why I have denoted both the subsystem by A. So that means after you remove this and uh, the, both the same particles, they will mix with each other and they will take the total volume B. But you will see that this is a um, reversible system. So if I what I can do, I can also, so let me uh, write down here. Uh, if we put the partition back to the same place, then we get the original system back. Original system back. So that means it is a reason. It is a so I mean if I put a partition again in the same place, I will again get the same system back here. Earlier it was not possible because I had different particles. I had uh, A particles here. I had B particles here. After removing A and B like mixed with each other, and if I put the partition, then I will end up with something like I will have some particles of A here, some particles of B here, and also some particles of A and some particles of B here. So I cannot really get A B type distribution for the previous cases we discussed. So that is why. So this is not uh, um, possible if I mean the earlier system which we discussed having two different types of gas particles then were not reversible. But now this is reversible. Uh, so reversible system. But for reversible system, we know the entropy should be zero. But here we are getting delta S is something uh, I mean positive. So this is not zero. So that is the problem that uh, this Gibbs paradox is about. So I mean this is what we know as Gibbs paradox. Uh, so you're getting what the point here is. Do you have any questions? So the reason that we like are having this entropy to be uh, not zero, this is I mean the entropy should be zero, should have been zero. So the reason is that like so in the case when we are discussing about identical system, we actually consider the partition function. Uh, if you see, we started our discussion by considering the partition function of distinguishable type of particles. So for identical system, uh, we should take the indistinguishable number of indistinguishable particle partition function. So then we will get the correct uh, answer for the entropy. So that is the problem which keeps resolved. So I mean not keeps. I mean so the uh, entropy which we will get after taking this partition function will get a Sackur equation, and that will give the correct answer for the entropy. So basically, we have to use this partition function to get the correct result. So yeah, mm, mm, uh, okay. So if I take the indistinguishable partition function, indistinguishable partition function, then I will have this um, uh, so the uh, for indistinguishable as we said at the beginning, it will be something uh, z to the power n over n factorial. So now if you take this, so with this if you take the entropy, which is uh, mm, yeah, with this new definition, you need to calculate what is kb ln zn plus u by t. So now it will give you the correct result, which is uh, so you have to follow the same method once again. You have to first get what is exactly log of zn. So partition function zn you have to calculate from here again. Um, so we know uh, what is z, and zn will be just z to the power n by n factorial for n distinguishable. So this thing. So we know z here as we showed it the some time ago. That is this relation. So you have this z. You take the power, its nth power, and divide by n factorial. Then then you have to put it in this relation to get log of z, and also you take the internal energy in the same way with the definition which we took, that is minus kVt square partial derivative of log zn by del t. So then you get the new entropy, that is from the indistinguishable partition function. So here I can just write the result here. So you have to follow the same exercise once again. So this will give you um, so uh, yeah, this will give you n kb log of v by n plus 3 by 2 ln kb. So this will give you, let me be more precise, more compact something. So this will give you n kb log of vt 3 by 2 over n plus some constant c0, where c0 uh, so where c0 is log of 2 pi m kb over h square 3 by 2 e to the power 5 by 2. So this is this is your uh, Sackur Tetrode equation. Now, if you take the case of identical system, which we considered n1 by v1 equal to n2 by v2, something n by v, you will get the change in entropy to be 0. So this is how the paradox was resolved. So I think, yeah, like we almost uh, got it. I mean, at the end. So you have to do the last bit of similar exercise which we just did before for the case when we considered the distinguishable partition function. So rest is this straightforward. So if you have any question, you can ask now, or if you if you don't have any, you can. Um, okay. Uh, do you have any questions on anything not understood? Anything, any issue, you can ask. Okay, if there is no question, we can meet again. We can. Uh, okay, you can uh, tell me if you have any problem. So until then, Nick, um, you can go through the assignments or your lectures. So yeah, so it's uh, So we are already done for today. So it's already, I mean, the time is up for today. So we can have the session, our discussion again next week in the usual time. So yeah, so yeah, see you.